Okay, hi everybody. So in this video, we're going to continue working with the mass spring oscillator that we've been working with. So for example, um, here we're looking at a little applet in a application called Mathematica. And this is the undamped mass oscillator, for example, where the friction damping coefficient here is pretty close to zero. I actually can't set it to zero without this app getting upset with me. So I set it as close to zero as I can, and we're getting this periodic behavior in our solutions that the mass is oscillating back and forth between its most rightward position and its most leftward position, and the amplitude of those oscillations is remaining constant. So it's going 1 unit to the left, 1 unit to the right, back and forth. And so now let's consider what happens if we put some external force on this. And so how I can do that is this. So we've got the spring, that's the green thing, which is bouncing back and forth. Excuse me, the mass is the green thing. It's bouncing back and forth, connected to this blue spring, which is connected to this red wall. And instead of connecting the other end of the spring to a stationary wall, we can introduce some external forces by moving around the other end of the spring. So I'm going to set the forcing amplitude to be 1/2 and the forcing frequency to be 4. And when we do that, we now see that we're adding an external force. The other end of the spring is connected to this red wall, which is now moving around, and that changes the dynamics of the system. So if I kind of step this back and hit play, we can see that the actual amplitude of this is shifting. So it's actually winding up, going a little bit further to the right each time, and going a little bit less to the left each time. We do have oscillating behavior, but the amplitudes are changing. So let's kind of see why that might be happening. So I am going to switch screens and take us into my iPad. Okay. Here we go. So we got my iPad. And so now what's happening is we no longer have a homogeneous solution because we're putting some external force. So now the force from friction, the force from the spring, and this external force of moving around the other end of the spring, they should all add up and equal the force exerted by the mass. So our equation now has a right side, which depends on time. And so let's consider the mass being 1, the stiffness coefficient to be 4, and now we have this forcing function over here, which this is acting as the moving other end of the spring. And so let's think about what our guess would be for the particular solution if we had a value for omega, which is like the frequency of how frequently the wheel is turning around, if that's equal to 4. So when we're finding guesses for the particular solution, recall our first step should always be find the homogeneous solution. So we would set up our characteristic equation, which would be the r squared plus 4 equals 0. And we've got our two roots that r is plus or minus 2i. So that would give us a homogeneous solution of C1 cosine of 2t times C2 times the sine of 2t. And coming over to the forcing function, which is now 0.5 cosine of 4t, since we have a cosine of 4t on the right side for the non-homogeneous forcing function, it would make sense that our guess for the particular solution would be something that has the cosine of 4t, some constant times the cosine of 4t, and we need to possibly include some constant b times the sine of 4t. And then we would compare our particular solution to the homogeneous solution and try and see whether we have resonance. And so since the homogeneous solution had two t's inside the trig functions, and this has 4t. Therefore, we don't have any resonance, and that's our particular solution. And so now let's consider what happens if the frequency, the value for omega, is no longer 4, but if we set that equal to 2. And if you're looking ahead, there might be something special about when omega becomes 2, because those were exactly our homogeneous solutions. So let me change the screen here and jump back into the applet that we were using in Mathematica. And so here we've got this forced mass spring oscillator. And I'm going to change the forcing frequency to 2. But if I set it actually equal to 2, this is going to get upset with me. So I'm going to set it to something close to 2. And now you can see that we've got really crazy behavior going on. And so what's happening is we have oscillations, but each time the system oscillates, actually the amplitude is getting larger and larger and larger. And if you let this play out over time, eventually the amplitude would get longer than the actual spring if you stretched it all the way out. So in fact, what would happen here is the spring would totally get ripped in half if we let it progress even further. So let's kind of see why we're experiencing those sorts of behavior in our solutions by coming back into my iPad. Here we go. And so with that picture in mind, if we were trying to come up with a guess for this particular solution, well, our first guess would be if the forcing function is 0.5 cosine of 2t, I would guess something that has cosine of 2t and sine of 2t in it. So I would guess a particular solution of a cosine 2t plus b sine of 2t. And now we definitely have resonance with the homogeneous part. We have a cosine 2t in both. We have a sine of 2t in both. So that means when we have resonance, like in this example, therefore we would need to multiply our particular solution by a factor of t. So I would get a times this factor of t cosine of 2t plus b times this factor t that we just multiplied by times the sine of 2t. And so that would be our particular solution. And then overall, our general solution would be the sum of the homogeneous solution and the particular solution. And now you can see why this spring is kind of blowing up in this case, because we have these t's over here. As t goes to infinity, the amplitude on this particular solution is getting infinitely large for both of these pieces. So now as t goes to infinity, the homogeneous part, that behaves nicely. The particular solution, the amplitudes are heading off to infinity. So now we can see what happens when systems have resonance. Really weird things can happen. And if you are curious about exploring some of these weird things, check out the last couple of slides. One of them is an example of how we could break glass by singing with our voices. So if you have a wine glass, it's made up of crystals that have a certain natural frequency in them. And if a person sings and their voice has the same frequency as the structure of the glass, you can snap the glass in half. And the other example is the case with a suspension bridge that was built in Washington State. And in that case, the oscillation, it got really windy and the bridge was oscillating with a frequency that was resonant with the construction of the bridge. And you can see that the amplitude of the oscillations of the bridge goes off to infinity and the bridge actually collapses. So if you're curious about investigating those situations, take a look at the last couple of slides. Otherwise, this wraps up the material in chapter 2. So let me know if you guys have any questions, just reach out.